1.6c divided by 1.63. Something doesn't feel right about that. I feel like you got a minus sign in the wrong spot. Give me a moment. Galilean relativity, then velocity of the, so it's shooting out at 0.7, it's coming back at 0.9. There is a problem here. Problem I'm having. Or the problem concerning this that I'm having. Let's think back to Galilean relativity. If I'm in a car going at 7 meters per second to the right, and the dad is throwing the ball backwards at 9 meters per second, how fast is the ball going relative to the ground? If this is the velocity of the car with respect to the ground, and this velocity of the ball with respect to the car, then the velocity of the ball with respect to the ground, is the velocity of the ball with respect to the car plus the velocity of the car with respect to the ground. So if that were, that's 7, that's -9, I'd get -2. But the difference is that I gave a different reference. Okay, I'm less trouble. Okay, nope, it's right. Because the equivalent would be not that. The equivalent would be if this is -0 or -9 equals, because that's velocity of the ball with respect to the rocket, that's our unknown plus. So our unknown would be -9 minus 7 or -16. Okay. All right, I'm good. Questions? It is amusing.
I think it's left me more confused, but it's okay.
Yeah. The big thing to remember is, first off, questions on Galilean relativity, about figuring out like the ball in the car. If you can establish that, then the equation that you would use would come out of that. There's going to be a denominator. And another thing here is that if the speeds we're talking about are much less than the speed of light, then this term right here becomes insignificant. And what we're left with is Galilean relativity. Because then it's just 1 plus something really close to 0. Let's just do more standard one, nothing going backwards. And since you all have calculators. Classic rocket. We'll make that planet X. The velocity of the rocket with respect to planet X is .8 times the speed of light. We'll have something happening here. Shooting forward, so the velocity, we'll make it a ball again. The velocity of the ball with respect to the rocket is 0.4 times the speed of light. What is the velocity of the ball with respect to planet X? I would like you to give it a shot on your own before we talk about it as a group. First thing, assume relativity is bunk and figure out what the answer is, and I think that will guide you. The numerator, you're going to either add or subtract the two velocities. These would be plus or minus. That would be multiplication right there. You got it?
I think so. 'Cause the top is just Galilean relativity, right?
Yep.
And that's just them multiplied, right? And these
Louise, you were looking at me like,
Oh, no, I think I have it. I
Oh,
don't know if it's
okay.
right, but I think I have it.
That sign will be the same sign as that.
Oh, okay.
Otherwise, you end up with something bigger than the speed of light.
Yeah.
Which the physicists are frowning upon.
Okay. That's what I just had. It was right.
Started out right. Looking at that. Oh, you lost your speed of light on top. It's gonna cancel out, that's 0.4C and 0.8C, so the C's cancel out down there, but it's still 0.8C there. And there you go. Unless you're doing one of those pesky theoretical things where they go, well, there exists a unit system where the speed of light equals 1. So if you've got Galilean relativity, again, I mean, you could think through it and still come up with the same answer, but those subscripts are the same, and so what I'm gonna be left with is the first and the last, which is what I want. And then put it, so that's Galilean relativity, and then special relativity is you're gonna take that and then divide by 1, and then the same sign, plus and plus, and then the product of the two velocities over the speed of light squared. And so we end up with dr is 0.4c plus rx is 0.8c, 8c. Divided by 1 plus 0.4c times 0.8c over c squared, which is 1.2c divided by 1.32. Questions? Yes?
So in what case would both of the signs be negative? Like when it's going backwards?
One was going backwards, and I gave you, if this were the velocity of B with respect to the rocket, then I'd have one negative, one positive. But because it's the velocity of B with respect to the Earth, we end up with 2 negatives. I don't think that really answers the question. It just, in circumstances, make it so. Again, I personally, if I could do it this way, then I do the pattern, which may not help you either. But. If something is going backwards, there's going to be a minus sign in there somewhere.
Okay.
what you're thinking. You're going, hey, I noticed a pattern here that everything that we've been doing, we always have, we're looking at things happening in the same direction or opposite the direction of movement. Maybe. He's throwing a ball parallel to the velocity of the rocket. Suppose it weren't parallel. Suppose there was a perpendicular part of it. In other words, you're in the rocket. And so we got some sort of X frame. S frame. I've got an S prime frame, and your object's being thrown in that direction. Where S prime is moving in horizontally, but the object is moving at an angle. Well, we have to break it up into parts. Do standard X, Y, Z. I know X prime is equal to gamma X minus how fast this thing is going. We'll go back to using ut. Y prime equals Y, Z prime equals Z, T prime is equal to gamma T minus UX over C squared. The primary relativistic effects are parallel to it, but we will have some messing around with it perpendicular to it. WX, Y. W is the velocity of, I'm just going to call it P. The velocity of P with respect to S prime. And then Vx and Vy, where the V is, using the same letters for different things. Velocity of the particle with respect to S. In the context of what we just did, S would be the Earth, S prime would be the rocket. They're just different reference frames. Before I go too far astray, now figuring out Vx, we've already done that. That's all of that stuff over there. It's the Vy part that I'm more concerned with. I know that Vy equals the change in y over the change in time. Vy prime, which is W1, is going to be the change in y prime over the change in t prime. Well, since y prime and y are the same, and the length contractions or length expansions are going to be in the direction of motion, that's just delta y over delta t prime, which is delta y over gamma delta t minus u delta x over c squared. So all I've done is, this is a specific time, I did change in time, which would affect x and t, thus the delta in front of it. If I multiply top and bottom by 1 over delta t, I get delta y over delta t. In the numerator and in the denominator, I get gamma 1 minus u over over c squared, delta x over delta t. Well, delta y over delta t is the change in y from the Earth's point of view, S point of view, over the amount of time that took it happened in S's point of view. It's just Vy. So Vy prime is just Vy divided by gamma 1 minus, right there, at the delta x over delta t. That's how fast the thing's moving. That's in the S frame, the Earth's frame. Then that's just the speed, so that's u v over c squared uvx. And I looked to make sure I didn't make a Carol's error. Okay. So now we could then translate things going all that way. Let's do a little bit of a plug jug here. The S frame, think of it as Earth if you wish. S prime, think of it as the rocket. The velocity of S prime with respect to S is 0.9 times the speed of light. Then I have an object here being thrown up at an angle. And so in the S point from the S point of view, velocity of particle or ball or piece of something